Welcome back, everyone, to the Deep Dive. Ready to dive into something electrifying today? We're going to be exploring the world of DC circuits.
Yeah, DC circuits. But don't worry, we're not going to get all like textbooky on you.
Absolutely not. In fact,
Okay.
we're going to be using this super cool interactive simulation. It's called Circuit Play.
Oh, yeah, circuit play. It makes learning about circuits actually fun.
It's a hands-on experience.
Yeah.
And by the end of this deep dive, you'll be able to, not just describe a basic DC circuit,
Right.
but you'll actually be able to analyze how all those different components work together.
Right.
To really create that flow of electricity.
And what's really fascinating is that understanding even these like seemingly simple DC circuits is like, it's like unlocking a secret code to how so much of our technology works.
It is.
I mean, think about it. From the smartphones in our pockets
Right.
to the power grids, like energizing our cities, it all comes down to the fundamentals of DC circuits.
It really does.
And I bet we can even like debunk some common myths about electricity along the way.
Oh, yeah.
You'll be the smartest person in the room at your next tech gathering.
Okay, so let's get right into it. Our main source for this deep dive is this awesome simulation Circuit Play. You can actually find it at website URL provided in the source. It's basically like a virtual playground where you can build your own circuits. You can use wires, resistors, batteries, a bunch of other components.
You can like drag and drop.
Yeah.
Connect them in different ways, see how the circuit behaves in real time.
That's the best part. You can see it all happening.
And what's really cool is that you're not just like building random circuits, you're actually learning how those different arrangements, affect the overall flow of electricity.
Right.
And specifically, we'll be diving into the concepts of series and parallel circuits and how they impact the circuit's resistance.
Yeah.
You might have heard these terms before, but we're going to like break them down, make them, understandable and actually really fascinating.
Yeah.
Yeah.
So before we get into all that, let's just kind of lay down some groundwork.
Okay.
First up, what exactly is direct current? Or DC?
Right.
We all use DC devices every single day, but, we might not know how they differ from the AC electricity that powers our homes.
Yeah. Well, imagine you have a battery.
Okay.
That's a perfect example of a DC source. In a DC circuit, the electrons flow steadily in a single direction, from the positive terminal of the battery to the negative terminal. It's like a one-way street for electricity.
Got it.
This is different from alternating current, or AC,
Right.
where the electrons are constantly changing direction.
Okay.
Yeah, like a busy two-way street with traffic going back and forth.
So when we talk about DC circuits, we're essentially talking about circuits powered by batteries, right?
Right.
And speaking of batteries, I've always wondered about this. There's this common saying like, does the current in a battery actually get used up?
Right.
Because it seems like, the battery's power dwindles over time, so something must be getting depleted, right?
Yeah. That's a great question, and it gets to like the heart of how electricity really works.
Okay.
It's not the electrons themselves that get quote unquote used up.
Right.
It's their potential energy.
Oh, okay.
Think of it like a ball rolling down a hill.
Okay.
The ball itself doesn't disappear, but its potential energy, which was high at the top of the hill due to gravity,
Right.
decreases as it rolls down.
So it's not the electrons themselves that are, disappearing for the battery.
Yeah.
It's their energy that's being transformed into other forms.
Exactly.
Like the power to run our devices.
Exactly. And here's another common misconception.
Okay.
That the current flowing from a battery is always constant.
Uh,
It's actually much more dynamic than that.
oh, really? So if the current isn't always the same, what does it depend on?
It all comes down to resistance.
Resistance.
Yeah. Think of it like a water pipe.
Okay.
The wider the pipe, meaning lower resistance, the more water can flow through, meaning higher current.
Okay.
Even if the water pressure, like the voltage from the battery, stays the same.
Okay, so in an electrical circuit, the battery provides the voltage,
Right.
which is like the electrical pressure. But the amount of current that actually flows depends on the total resistance.
Of the entire circuit.
The entire circuit.
Right. Yeah.
Okay. So how does this resistance actually work in a circuit?
Right.
Back to our circuit play simulation.
Yeah.
We have these components called resistors that we can add to our circuits.
Resistors are the key to controlling the flow of current in a circuit.
Okay.
They do exactly what their name suggests.
Okay.
They resist the flow of electrons.
Okay, so how do resistors affect the current in a circuit?
Right.
Let's say we start connecting these resistors in different ways.
Right.
For instance, What happens if we connect them in a single line, one after the other?
That's what we call a series circuit. And it has some interesting effects on the total resistance.
Interesting. And what if we arrange those resistors side by side, like, parallel lanes on a highway? Would that change things up?
Absolutely. That's called a parallel circuit.
Yeah.
And it introduces a whole new set of dynamics, when it comes to resistance and current flow.
Okay.
Yeah. But we'll save that discussion for the next part of our deep dive.
Right.
So you're curious about how those resistors behave when they're connected in a line, one after the other, like in a series sequence.
Exactly. Yeah. What happens there?
Well, imagine a single lane road where traffic has to pass through each section one at a time.
Okay.
Each section kind of adds to the overall distance and travel time, right?
Right.
In a series circuit, it's similar. Each resistor contributes to the total resistance, making it harder for that current to flow.
So if you add more resistors in series, the total resistance increases.
Yep.
And the current decreases.
Precisely. And the way we calculate that total resistance is pretty straightforward. You simply add up the resistance values of each individual resistor.
Okay, so you just add them all up.
It's like adding up the length of each section of that single lane road to get the total distance.
That makes sense. Now, what about those parallel circuits we mentioned earlier?
Yes.
Those resistors arranged side by side, like, multiple lanes on a highway,
Mm-hmm.
I have a feeling it's not as simple as just adding them up.
You're right. Parallel circuits are a bit more nuanced.
Okay.
Think about it. If you have multiple lanes on a highway, traffic can flow more easily even if each individual lane has a speed limit.
Right.
Similarly, in a parallel circuit, the total resistance actually decreases as you add more branches. It's like opening up more paths for the current to flow.
So connecting resistors in parallel actually creates less overall resistance.
Exactly.
And that allows more current to flow through the circuit.
Yep.
If that's the case, wouldn't that put more strain on the battery?
It's true that adding parallel branches increases the total current drawn from the battery. But remember, the battery is designed to provide a certain voltage, which is like that electrical pressure. It's the interaction between that voltage and the circuit's resistance that determines how much current actually flows.
Okay, that makes sense. But going back to the parallel resistance calculation, I imagine it's a bit more complex than just adding the resistances together, like we did with the series circuit.
You're right, the math is a bit different for parallel resistors.
Okay.
Instead of adding the resistances directly, we use a reciprocal formula. But don't worry, it's not as complicated as it sounds. The key idea is that each parallel branch provides an additional path for the current, and those paths work together to reduce the overall resistance.
I'm curious, though, if adding parallel branches decreases the resistance, wouldn't we be able to keep adding more and more branches and eventually get practically zero resistance? Would that mean we could have a circuit with, like, almost unlimited current?
That's an interesting thought, but unfortunately, it doesn't quite work that way in reality.
Okay.
While theoretically you could keep adding parallel branches,
Yeah.
every component in the circuit, including the wires themselves, has some inherent resistance. Plus, there are practical limits to how much current a battery can actually supply.
So even though the concept of, like, decreasing resistance seems like it could lead to infinite current, there are real-world constraints that prevent that from happening.
Right.
It's like trying to drain a pool by adding more and more hoses.
Right.
Eventually, the pool's pump just can't keep up.
Exactly. And even before you reach those limits, you might encounter issues like overheating wires or even damage to the battery.
Right.
So while parallel circuits are incredibly useful for controlling current and distributing power, there's no such thing as a free energy lunch.
All right, that settles that. Now, I remember you mentioned some common misconceptions about electricity earlier.
Yeah.
We already busted the myth about current getting used up. What's another one that often trips people up?
Another common misconception is that a battery always delivers a constant current, regardless of the circuit it's connected to.
I've definitely heard that before.
Yeah.
It seems intuitive, like the battery just, pumps out a fixed amount of electricity.
It's a tempting assumption, but it's not quite accurate. The battery provides a constant voltage, which is like the electrical pressure pushing the electrons along. However, the actual current that flows depends on the resistance it encounters in the circuit.
So it's like a water pump that maintains a certain pressure.
Yeah.
But the actual amount of water flowing through the pipes depends on how wide or narrow those pipes are.
That's a great analogy. A higher resistance restricts the flow of current, just like a narrow pipe restricts the flow of water. And conversely, a lower resistance allows more current to flow, like a wide pipe. It's this dynamic relationship between voltage, current, and resistance that makes DC circuits so fascinating.
Okay, I think we've covered a lot of ground here.
Yeah.
We've, explored series and parallel circuits, busted some myths, and even delved into that relationship between voltage, current, and resistance.
Right.
But what are some real-world examples where these concepts come into play?
Mm-hmm.
I mean, how do these principles actually translate into the devices we use every day?
Think about the volume knob on your headphones or stereo.
Oh, okay.
You use it all the time to adjust the loudness, but have you ever considered what's happening inside that knob?
I have to admit, I haven't given it much thought. I just, turn it up or down depending on how loud I want the music to be.
Well, that knob is connected to something called a variable resistor or a potentiometer.
Okay.
By turning the knob, you're actually changing the resistance in a specific part of the circuit,
Uh-huh.
which in turn controls how much current reaches the speaker.
So increasing the resistance lowers the volume.
Precisely. A higher resistance restricts the current flow, resulting in a quieter sound. Conversely, lowering the resistance allows more current to flow, boosting the volume. It's a simple concept, but incredibly versatile.
Now I'm thinking about dimmer switches for lights.
Yeah,
Do they use the same principle?
you're on the right track. Dimmer switches, especially those for traditional incandescent light bulbs, use a type of variable resistor to control the brightness. By adjusting the resistance, they regulate the amount of current flowing to the bulb's filament, which in turn affects its temperature and the intensity of the light it produces.
But what about those newer LED lights?
Right.
I know they're much more energy efficient.
Yeah.
But I'm curious how dimming works for them. It
Yeah.
seems like it would be different than simply changing the resistance, like with the old school bulbs.
You're absolutely right. LEDs are a different beast altogether. They require very precise control of the current flowing through them, and simply varying the resistance wouldn't achieve the desired effect.
So how do LED dimmers work?
They use something called pulse width modulation, or PWM. Essentially, the dimmer rapidly switches the current on and off thousands of times per second.
Wait, so switching the current on and off makes the light dimmer? That doesn't seem very intuitive.
It might seem counterintuitive, but it works because of the way our eyes perceive light. By controlling the ratio of on time to off time, the dimmer effectively reduces the average amount of power delivered to the LED, making it appear dimmer to our eyes.
So it's not actually reducing the current, it's just delivering it in like extremely rapid bursts that our eyes perceive as a continuous but dimmer light.
Exactly. It's a bit like rapidly blinking a flashlight on and off. If you blink it fast enough, your eye just sees a dimmer, steadier light.
Huh.
Pretty clever, right?
That's amazing. It's fascinating how something as seemingly simple as a dimmer switch actually involves like such sophisticated electronics.
It just goes to show that even the most commonplace devices we use every day rely on these fundamental principles of DC circuits and resistance control. And as technology advances, we can expect to see even more creative and innovative applications of these concepts.
Okay, so we've debunked some myths, explored series and parallel circuits, and even delved into real-world applications like, volume knobs and dimmer switches.
Right.
What's next on our deep dive into DC circuits?
We've laid a strong foundation, but there's still so much more to uncover. In the next part of our deep dive, we'll tackle the concept of power and explore how resistance plays a crucial role in determining how much power a circuit uses. We'll connect it back to those watts you see on light bulbs and appliances, and maybe even bust a few more myths along the way.
Okay, so we've covered a ton in our exploration of DC circuits, but there's one more crucial concept we need to tackle: power.
Absolutely. Power is it's the rate at which electrical energy is converted into other forms of energy, like heat, light, or motion. And it's something we encounter constantly in our daily lives.
Right.
Whether we're talking about the wattage of a light bulb, the horsepower of an electric car, or even like the battery life of our smartphones.
Okay, so we all know that like a 100-watt light bulb uses energy faster than a 60-watt bulb.
Mm-hmm.
But where does resistance fit into this whole power equation?
Well, resistance plays a crucial role in determining how much power is dissipated in a circuit.
Okay.
Think of it like the higher the resistance, the more difficult it is for current to flow through a component.
Okay.
And that difficulty translates into energy being converted into heat.
So a component with high resistance is going to generate more heat than a component with low resistance.
Yeah.
even if the same current is flowing through both.
Exactly.
That's good to
It's
know.
like trying to push a heavy object up a hill versus pushing a lighter object the same distance.
Okay,
You'll expend more energy pushing the heavier object,
Okay.
even though the distance is the same.
that makes sense. So is there a way to actually calculate power based on resistance and current?
There are actually a few different formulas for power,
Okay.
but the most useful one in this context is power, which is represented by the letter P equals current, represented by I squared times resistance, represented by R.
So if you know the current flowing through a component and its resistance, you can easily calculate how much power it's using.
Exactly.
All right, so let's try that formula out.
Okay.
Let's say we have a simple circuit with a 12-volt battery and a single resistor with a resistance of 10 ohms.
Okay.
First, we need to find the current flowing through the circuit, right?
Right. We can use Ohm's law for that voltage represented by V equals current represented by I times resistance represented by R.
Okay.
Rearranging that formula, we get I equals V divided by R. In this case, that's 12 volts divided by 10 ohms, giving us a current of 1.2 amps.
So now we have the current.
Yep.
We can plug that into our power. Formula power equals 1.2 amps squared times 10 ohms.
Which gives us a power dissipation of 14.4 watts. So our 10 ohm resistor is converting 14.4 joules of electrical energy into heat every second.
Now, what if we swap out that 10 ohm resistor with a 20 ohm resistor?
Okay.
Would that change the power dissipation?
Absolutely. Let's calculate it.
Okay.
With a 20 ohm resistor, the current would drop to 0.6 amps, 12 volts, divided by 20 ohms. Plugging those numbers into the power formula, we get 0.6 amps squared times 20 ohms, which equals 7.2 watts.
Wow, so doubling the resistance actually cut the power dissipation in half.
Yeah.
That's a pretty significant
It
difference.
really highlights the importance of understanding the relationship between resistance and power.
Yeah.
If you're designing a circuit where heat dissipation is a concern, you need to carefully consider the resistance values of the components.
So what are some practical examples of where this knowledge comes in handy?
Well, think about those old incandescent light bulbs.
Yeah.
They get so hot because their filaments have high resistance, which intentionally converts a lot of electrical energy into heat-producing light as like a byproduct.
Right, which is why they're not very energy efficient. LED lights, on the other hand, are much more efficient because they have lower resistance and produce much less heat.
Exactly. And those space heaters that use glowing red coils to warm up a room,
Yeah,
those coils have extremely high resistance to maximize heat output.
that makes sense. It also makes me think about electrical safety.
Right.
If a wire has too much resistance, it could overheat and potentially cause a fire.
That's a crucial point. Electrical wiring is designed to have low resistance to minimize heat generation.
Okay.
But if the wiring is damaged or overloaded, the resistance can increase, leading to dangerous overheating.
Right.
That's why it's so important to use the correct gauge of wire for the intended current and never overload circuits.
So we've really explored a lot in this deep dive into DC circuits. We've tackled the basics of voltage, current, and resistance, debunked some common misconceptions, and even touched on real-world applications and safety considerations.
Yeah, we've really gone from just describing simple circuits to like analyzing their behavior and understanding how they underpin so much of our technology.
I feel like I have a much deeper appreciation for how electricity works now.
And that's what's so fascinating about DC circuits. They're the foundation of so much of our modern world.
It really is.
And understanding them just opens up a whole new level of insight into how things work.
It's like we've unlocked a secret code to understanding the flow of energy all around us.
And that's the beauty of a deep dive. It's about taking a seemingly complex subject and breaking it down into understandable and even fascinating concepts.
So as we wrap up this episode, I encourage you to keep exploring, keep asking questions. The world of electronics is full of amazing discoveries waiting to be made.
And who knows, maybe you'll be the one to make the next breakthrough. Until next time, happy circuit building.